A continuación, la sesión se basa en presentar, o hemos pensado en una sesión que pretende presentar lo que llamamos casos pioneros de aplicación de inteligencia artificial. Para ello hemos seleccionado unos cuantos campos, unas aplicaciones que veréis distintas en las áreas más representativas o quizá más tractoras de la inteligencia artificial a día de hoy. En primer lugar, veréis un caso de aplicación concreto de Machine Learning donde el conjunto de entrenamiento tiene la particularidad de ser bastante poco poblado e imbalanceado. En la segunda ponencia veremos un caso concreto de aplicación de técnicas de NLP para el diseño, para asegurar que el diseño de intents en el desarrollo de chatbots es el correcto. Y finalmente veremos una aplicación para inspección de neumáticos basada en Deep Learning, de la mano también del Centro de Visión por Computador. Sin más, vamos a empezar, vamos a escuchar los interesantes casos y empezamos primero con Jaume Cardús y Maryam Rahbaralam, que nos presentarán un caso concreto de predicción de averías a corto plazo en la red de tuberías de agua. Jaume Cardús es informático por la UPC, es ingeniero industrial por la UPC y máster en gestión de agua. Con más de 20 años de experiencia en Aigües de Barcelona, actualmente lidera el desarrollo de nuevos modelos de priorización de inversiones. Maryam es Data Scientist en el Centro de Visión por Computador y obtuvo su máster en la Universidad Pompeu Fabra y la Universidad Politécnica.
Doctorado, sí.
Pues les damos paso a ellos. La presentación en este caso será en inglés.
Good afternoon. It's a pleasure to be here and have the opportunity to explain, together with my BSC colleague, our machine learning project. Nowadays, Aigües de Barcelona is supplying almost 3 million inhabitants. To do so, we have to manage 6 drinking water treatment plants, 77 water tanks, 84 pumping stations, and almost 5,000 kilometers of network pipes. In any water supply company, the network represents more than 60% of the value of the system assets. It's obvious then that we will stand out in our management if we renew those pipes which are more likely to fail, and also if we keep on working for minimizing network failure consequences. Here you can easily see the consequences of a major failure we had in 2016. The thing is that although our network is highly meshed, it's impossible to avoid having temporary social and environmental impacts in each failure. And the same happens to any water supply company. We all have to hurry up to repair as fast as we can with the minimum cost all the failures. And we also have to plan the renewal of those pipes with the most higher potential, ensuring the maximum investment return. And it's not easy. It's not easy because the network runs underground, and so far it exists no device which can give us any performance data for each pipe. Therefore, preparing a good renewal plan is strategic for all water supply companies, but at the time it's very difficult. Historically, we prepare our yearly renewal plan by comparing two predicted financial scenarios, the renewed scenario and the no-renewed scenario. We did that for all the inventory pipes in order to identify those with the higher financial predicted return. In 2017, we developed and started using our sustainable development prioritization models. Thanks to that, we now renew the pipes with a predicted highest overall social, environmental, and financial return. We have been using a Poisson regression model for the short and for the long-term failure potential predictions. But it was our concerns about the social and the environmental consequences of each failure which lead us to develop a machine learning solution for the short-term failure predictions. Here you can see the results of the Poisson regression model. It gives the evolution in time of the ratio of failures per length per year of each material. You can see that it predicts a very different behavior between materials. But notice that it only used two features, the edge and the material. Well, now we can say that we have already used in our 2020 renewal plan our machine learning solution for the short-term prediction, and we now know that it's 3 times better than the Poisson model. As Maryam will tell you, we are also working in a better long-term prediction, taking profit of all the bunch of data we have already have. As you may know, there is no machine learning if there isn't good data. No? That's why the first thing we did was setting up an expert committee for them to discuss and finally suggest the most failure-related features. And we managed to obtain the 85% of those. To the most common inventory features, the amount of material length, we add the number of failures of each pipe, the number of near repairing operations, the percentage of length running below sidewalks, below green zones, below heavy traffic streets, the number and age of each connection to each pipe. You also include the yearly average pressure and its simulated amplitude and stress. Moreover, we include the transmitters of temperature and pressure that are more likely related with each pipe. And finally, we include the ascendant pipe code, as some pipes are pieces of a largest original one which has been divided with time due to different reasons. No? And it needs work, a lot of work, and you need to dirty your hands. One key issue was undertaking the geospatial matching process to obtain a lot of the features I have already explained, and also cleaning all the data before and after all the gathered data was fused with the rest of the inventory of features. The resulting data set were BSC starting point. Maria?
Thank you. Thank you, Jaume, for your presentation. Sorry.
Is that one?
Yeah. Okay, here we start our collaboration with Aigües de Barcelona because we believe that feature engineering part is really important. Because in this way we can put the domain knowledge into algorithmic knowledge. We can do it alone at the BSc, and domain experts don't know the mathematical parts. So by this way, we start our collaboration to integrate domain knowledge into the algorithmic knowledge. At the BSc, we specialize in high-performance computing and manage Mare Nostrum, which is one of the most powerful supercomputers in the world. BSc is at the service of research, community services, and industry, which requires HPC resources. At the BSc, we manage Mare Nostrum, but actually 10% of 500 people work here. The rest, like me, are researchers in many different areas. So let's start by looking at the problem that we want to solve here. As Jaume explained, we want to predict the pipe failure. So we have to predict that a pipe has failure or not. So here we have a typical binary classification problem, but to overcome these challenges, to solve these challenges, we have to overcome two challenges. The first challenges would be the data, because the data that we have is highly imbalanced. So it means that if I will predict no failure, I will be more correct in more than 99% of the time. So we believe that we have to use some technique to oversample our data. We use a smooth synthetic minority or sampling technique, which is create the new minority classes between existing two minority classes. So by this way, we make our data set more balanced. Another challenge that we have here is that the problem is time dependent. So it means that we have to be careful about the data manipulation for training. We employ a specific cross-validation technique by considering that we don't want to use the information from the past. At the first, we split our data into three parts: train, validation, and test. The test is kept away, and we're working with the training part, the rest part. So we use 5-fold cross-validation by considering that we don't see the information from the past. So we get average of all these 5-fold, and we obtain the final cross-validation score. Another thing that we believe is that we can solve the imbalanced data set not just only by resampling the sample, but also by rebalancing of target, which means that we don't want to see just the failure of the next year, but also we want to see the failure of the next year. So in this way, we believe that we can reduce the effect of the imbalanced data set that we have. Having prepared the data set, we want to employ the classification method, and we want to evaluate the performance of our model. To evaluate our model, we use 3 matrices. The first one is precision, because false positive are bad. The second one is recall, because false negative are worse. And we use another score, which is the MCC, Matthews correlation coefficients, which gives us the balance ratio of 4 categorical confusion matrices: true positive, true negative, false positive, and false negative. And then we employ classification method. Out of many models we evaluated, we choose XGBoost because it gives us the best score, and logistic regression because it is more understandable. Let's choose some result. Here we obtain a probability between 0 and 1, and we choose a threshold to make a binary choice. But it depends on the maximum MCC that we get. The maximum MCC is 0.28, and the precision is 0.25. It is worth mentioning that the precision for a short-term prediction with Poisson model that we got before was 0.04. So we see a good improvement here. Then we plot all of the scores as a function of this threshold, and we observe interesting things. We see that we have a flattish MCC, so we believe that this flattish MCC allows decision makers to choose from a wider range of the threshold. So if, for example, decision makers want to have a higher recall or higher precision, now it has a safe range of threshold. Here I want to show you some more results. we plot all of the scores as a function of the different number of years from 1 year to 4 years. And as we expected, by target resampling, we see that we get a higher MCC and higher precision and almost very constant recall. So in this way, we can say that by target resampling, we can reduce the highly imbalanced data set. Those are for the XGBoost model, but I want to show you some result about the logistic model, which is really important. Here we want to help our decision makers to have a more understandable result. So we did some feature importance, and we see that some features have a high impact on the pipe of failure, which was edge of the pipe pressure and the variability of temperature. By using the concept of odds of failure, we see that for a 10-year older pipe, the odds of a failure increasing by 25%. And for 15 meter more pressure, this odds of failure increasing by 17%. And for a pipe completely under green zone, we see this odds of a failure increase by 32%. And the variability of the temperature has a 60% more in odds of the failure. Okay, we did all of this to make a decision, but we believe that decision makers need to make a decision not considering just by short-term prediction, but also long-term prediction, and they have to know that the impact estimation. So the intersection of these three areas gives the best decision for our decision makers. In this project, we address the short-term prediction, but we believe that to improve this short-term prediction, we need more and better data. In order to see or have a better insight in long-term prediction, we believe that by using different kind of models like survival probability models, we can have a better insight in long term. As you can see here, we have a preliminary result with using the Cox model, and we got a continuous survival time, and we estimate the lifespan of each pipe. And in order to estimate the impact, estimate of the failure, we believe that we can use some artificial intelligence method in which we can design artificial agent learns the action which minimizes the risk. So we believe that by doing this all three concepts, we can make a best decision. Thank you.